Hey Hadley, this is a video lesson on lines and angles, one of the units in our grade 7 math curriculum. We're going to start by learning some vocabulary so that we have some words that we can use when we're talking about lines and angles. We'll then define different types and learn how to name them. We're going to learn how to use and read from a protractor. We'll learn properties of lines and angles that are going to help us solve different questions that we might encounter. And then we'll solve some practice questions. So let's get to it. Here's a list of different words that we use when we are talking about geometry, especially when we're talking about lines and angles. In the bottom there, you'll also see some symbols that are going to come up. It'll be important for you to come back to this slide and just check out these words and make sure that you're familiar with them. The first word we're going to learn is point. Pretty simple, right? A point is just a fixed location in space. It's actually not something that we can measure because it has no dimension. There's no length to it, there's no width to it, so we can't take a ruler and measure it. What we do know about it is that we can use it as a starting place for other points in space. We can label it with a name, like A. Now that I know what a point is, suppose I make a second point, and then I use that as a way of connecting those 2 points. When I connect 2 points with a line, that's what we call a line segment. It has a dimension now. We can take a ruler and we can measure the distance between those 2 points. That word segment just means piece. So what I actually have is a piece of a line. And that brings us to our next word. Maybe you've been calling what I just showed you a line your whole life. But now you know that a line segment is only a piece of a line. That must mean that a line is actually longer. And it is. A line is a continuous set of points going on forever in both directions. That means if I added points to my line, I can continue to add points over and over and over again. And if I continue to do that, what I actually get is a line. And an actual line, in theory, goes on forever. It doesn't stop. That's what a line is. So we know a line goes on forever in both directions. And we know that a line segment has 2 endpoints. A ray is a type of line that has one endpoint, but that goes forever in the other direction. We use an arrow on the other end of it to show that we understand that technically this line goes on forever, but space on our page is limited, so we need to stop drawing our line somewhere. The last thing we would want is to keep drawing this line off our desk and up the walls and out the front door and down the street and past the post office and, well, you get the idea. Next up is one that you've heard before, a vertex. Let's say we have 2 rays that are traveling through space like shooting stars, and suddenly those stars just hit each other. That point where the 2 rays meet is what we call a vertex. And we can measure the distance in between those 2 rays in something that we call degrees. And when we do that, that is what we call an angle. Okay, so we've learned some words that can help us when we talk about lines. Let's talk about how we would name angles now that we know what they are. When you see rays and angles in math questions, you're likely going to see that most of the time they have letters next to them. So how can we actually name them? There's actually a convention or a rule for how to do that. We need to use alphabetical order whenever possible. So we always start with the letter that would start first in the alphabet. And when we call the angle, we use the letters in this order: ray, vertex, ray. In other words, the letter for the vertex is always the middle letter that we use in our angle. So how would we call this angle? Well, if you were speaking, you would say this is angle ACB. Notice I started with A because it's first in the alphabet. The vertex C comes next, and then I say the other ray, B. And so this is ACB. If you were writing, sometimes you'll see in writing that we use this little symbol, and that would be the same thing, angle ACB. Types of angles. We're starting with the right or square angle, one that you've surely seen before, but I can't stress how important it is. So when you start with a vertex and you have a ray that goes straight up and another one that goes straight out to the side with that little square in the corner, that tells us that this angle measures exactly 90 degrees, and that's what a right angle is. We see right angles in time when we're talking about blocks of 15 minutes. It's helped us make sure that our buildings are straight up and don't fall over. It helps us define what perpendicular means, and it helps us locate things in space. When you think of a graph, well, that looks like a 90-degree angle as well. So its importance cannot be stressed enough. Now the next one is one that we don't usually see. We call it the straight angle. Let's say I have a 90-degree angle on one side over here, and then I flip it and have another 90-degree angle right back to back. What I've just created, obviously, is 90 plus 90, which is 180 degrees. So that tells us that if I was to measure a straight line, which is two 90-degree angles right next to each other, what I actually have is 180 degrees. Okay, well, let's take this a bit further. If I know that when I have two right angles back to back, what I actually have is 90 degrees plus 90 degrees is equal to 180, what happens if I added another 2 on the bottom side of that line? Well, what I would have is another 90 plus 90, or four 90s added together, and if I did that, I would get 360 degrees, which is also known as a circle. Therefore, we know that a circle has 360 degrees in it. So far, we've only talked about right angles, really, and how they connect to each other, but it's pretty clear that rays can meet in a whole bunch of different ways. So we've already talked about how we can have a straight angle, which is two 90s back to back, or measuring exactly 180 degrees. But what if we have less than 90? Well, we call that an acute angle. And if we know that we can have less than 90, that means we must have bigger than 90. So anything between 90 and 180 degrees is what we call an obtuse angle. And if we know then we have 180 degrees, anything that's between 180 and 360 is what we call a reflex angle. And you'll notice that a reflex angle almost looks like an obtuse angle, but really it's when you measure the opposite side of that angle. So we know what different types of angles are, we know how to identify them, we know how to name them. How do we actually measure them? To do that, we use a tool that's called a protractor, and it looks like this. It is a half circle with a straight line at the bottom, and that must mean that a protractor can measure an angle equal to up to 180 degrees because it's a half circle or a straight line. And this is how we use it. We start by aligning the protractor's center point to the angle that we're trying to measure's vertex. So you can see that little center point circle in the middle. We make sure that one of the angle's rays follows the protractor's baseline. Okay? Then we're going to read the measurement where the second ray passes through the protractor. In this case, it's exactly 45 degrees. One thing to notice is that because the protractor spans 180 degrees, that means that there is a 0 degree mark on either side of the protractor. It's very important that when we're measuring, we always start from 0 and not the bigger 180 degree line so that our angle is correct when we're measuring. Knowing how many degrees an angle measures can actually help us when we don't have a protractor. Properties of angles are facts that are true about angles. I like to think of them as little tricks that we can use when we know some information, but we don't have all the information for how many degrees an angle measures, and we don't have a protractor to help us. The first one that we're going to look at is called complementarity. So let's say we're given a 90-degree angle, and we know that that measures exactly 90 degrees. And then we're told that there's a ray that cuts that 90-degree angles at, for example, let's say 30 degrees. We can use the property of complementarity and figure out that what's left over has to measure that full 90 degrees minus 30 degrees, which is going to leave us with 60 degrees. And what we can say is that 60 degrees is the complementary angle to 30. In other words, the two angles complement each other to make 90 degrees. The next one is called supplementarity, or the property of supplementary angles. If we know that a straight line measures exactly 180 degrees, and we're told that we have a ray that cuts that angle at, let's say, I don't know, 80 degrees, then we can tell pretty quickly that what's left over has to measure that 180 degrees minus the 80 that we have, which is equal to 100 degrees. So we can say that 100 degrees is the supplementary angle to 80 degrees. The next property is called the property of vertically opposite angles. Let's say we have two rays that cross each other and they form what looks to be kind of like an X. What that gives us is four different angles. 1, 2, 3, and 4. We can say that angles A and B, the ones that are opposite to each other, are vertically opposite and therefore congruent to each other. Remember that congruent is just another word for equals. So angle A is equal to angle B. And because the other two angles, C and D, are also vertically opposite from each other, they are also congruent or equal to each other. So angle A and B are equal, and angles C and D are equal to each other because they are vertically opposite angles. Now, what if we had two lines that followed the same path, just in a different part of space? Meaning that no matter how far we travel down those two lines, they will never hit each other, never form a vertex, never cross. We call those lines parallel. In writing, we sometimes use the little symbols for parallel to show that they are. And if we were drawing directly on lines, we sometimes use little arrows to show that yes, those two lines are parallel and they'll never meet. Okay, time to get even more complicated. What if I said that there was a third line that went through those two parallel lines? Well, we would call that a transversal because it transverses those two parallel lines. And you can see that what gets created is actually four different angles around each parallel line. And you might be thinking to yourself, if I add up A, B, C, and D, I would have a circle which would measure 360 degrees. And the same would be true if I added up E, F, G, and H. And you're right, that is true. But I can't say what each of those angles are because they're not 90 degrees. Some of them are obtuse, some of them are acute. So how can I figure out what each of them is? It turns out that parallel lines and transversals actually have their own properties, which makes it easy to figure out what each one of them measure. The first property of parallel lines and transversals is called corresponding angles. Corresponding angles are the angles around the parallel lines that are in the same place. These angles have equal measurements. So what does that mean? Well, we can see that angle A is on the top left of one parallel line, and we can also see that angle E is on the top left of the other parallel line. Because those are in the same place, they are equal to each other. They are corresponding angles. The other corresponding angles in this situation would be angle C, which corresponds to angle G, angle B, which corresponds to angle F, and angle D, which corresponds to angle H. Those four sets of angles are equal to each other because they're in the same position, which we call corresponding. The second property of parallel lines and transversals are called alternate interior angles. So again, here's my transversal. And the property says that alternate interior angles are the angles on the inside of the parallel lines on opposite sides of the transversal lines. These angles are equal to each other. So what does that look like and what does it mean? Well, we can see that angle C and angle F are inside the parallel lines, but on the opposite sides of that transversal line. That means that angle C and angle F are equal to each other. So are angle D and angle E. They are on the inside, interior of the parallel lines, but on opposite or alternate sides. Therefore, angle C is equal to angle F, and angle D is equal to angle E. That's the property of alternate interior angles. The last of our three properties for transversals says that interior angles on the same side of a transversal line add up to 180 degrees. What does that look like? Well, if you look at angle C and angle E, you can see that they're both on the inside or the interior of the parallel lines, and they're on the left-hand side of the transversal line. Also, angle D and angle F are on the inside of your parallel lines, and they're on the right-hand side of the transversal line. So what this property says is that if I added up angle C and E together, I would get 180 degrees. And the same is true if I added up angle D and angle F together. How is this helpful to me? Well, it's helpful because let's say I knew that angle D is 110 degrees, but I don't know what angle F is. I could figure that out very quickly because I can say that 180 degrees minus 110 degrees is going to be what's left over, and what's left over is going to be the measure of angle F. So that's how that is helpful. So now that we know these properties of angles and how they can be helpful to us, we can actually solve when some of the angles are missing, but we know some others. We can use these properties as reasons, or what we call justifications, when we need to find those missing angles. Now keep in mind, I'm going to be solving this one way, but there are many strategies that you can use and many different justifications that you can use in order to get your final answer. As long as your reasons make sense for why you think the missing angle is what it is, you will be right. Okay, let's try the first of two questions. This one says, solve for the missing angles without measuring, meaning do not use a protractor. Give a reason, justification for why that angle measurement is true. So if we can't use a protractor, then we have to rely on the properties, the facts about angles that we just learned. So on the left-hand side here, you're given a picture. You can see that we're only given one angle and we need to solve for the other three. On the right, we have what's called a justification table. That's where we're going to write down the measurements and give our reasons for why they are. Now I'm going to start with angle GKJ. You don't have to, but that's the one that I'm going to start with. And I can see that that angle, GKJ, is right across from the angle that I know, HKI. So that means that automatically I can say that this angle is 93 degrees. And the reason, the justification, is because of that property called vertically opposite angles. We know that when two angles are vertically across from each other, they are equal. So there's no calculation there at all. I can just go ahead and say that it's 93 because they are vertically opposite. The next one I'm going to do is IKJ. So IKJ is on the right-hand side. And I know that the answer to that is 87 degrees. And the reason I know that is because of another property that we learned called supplementary angles. If you remember, a supplementary angle is when you know that a straight angle, like we have when we look at H all the way to J, measures 180 degrees, and we know a part of it, 93. So if we know a part, we can figure out what's missing by taking 180, subtracting 93, and we get 87. Now there's only one that's left, and there's actually quite a few different ways to solve this one. But if we just found out that IKJ measures 87 degrees, then we can use the same property that we did before, the vertically opposite, right? And say that this one has to be 87 also because it's directly across from the one that we already know. So you can see how we found out one and then use that to find out the next. But there's another way that you could have done that as well. And the other way you could have done it is actually use supplementary angles, right? Because if we know HKI is 93, and we know that G all the way to I is a straight line, and we know that that measures 180 degrees, we can subtract 93 from 180 and get 87 that way too. So it really doesn't matter how you justify it as long as it makes sense. And there could be even a third way to put this down as well. If we know that a circle measures 360 degrees, then we could take 360 and subtract 93, subtract 87, and subtract 93 again, and you'll get 87, which is what left over. In fact, that is one way that we can verify our work, right? If we add up 93, 93, 87, and 87, does that equal to 360 degrees, which would be the whole circle? The answer, of course, is yes, it does. So we know that our work is right. Okay, last question. We have a parallel lines and transversals question, so we know we can use some of those properties to help us. We're only given one angle here, HFN, which is equal to 122 degrees, and we're supposed to find EFM and EGQ. So I'm going to start with EFM, and I know right away that that's got to be 122 degrees, and the reason is because it's vertically opposite from the one that's given to us, HFN. So because that's given, and I know it's right on the opposite side, I know that one has to be 122 degrees. All right, EGQ, the other question mark, well, that has to be 122 degrees also. And the reason is because it's corresponding. Corresponding, if you remember, means that it's in the same position on the same side of the transversal and next to its other parallel line. So it's corresponding to EFM. So that's it. That's the question. Now, I think we can do a little bit more. So I thought we would solve for every other missing angle as well. I'm going to start using dots to show you which angle I'm working on because it can get confusing very quickly. So the first one I'm going to work on is this one, HFM here. And I know that that has to be 58 degrees. And the answer is, there's a little calculation involved, but I can see that if the one that I just found here, 122, is inside the parallel line, just like HGQ is, HFM is, then that means I can say 180 degrees minus 122 is equal to 58 because of my property that says interior angles on the same side of a transversal add up to 180 degrees. Okay? So that has to be 58 degrees. The next one I'm going to work on is HGQ, which is this one right here. And again, there's different justifications you can use. I know that it has to be 58 degrees either way, and the reason that I'm giving is that it's corresponding to HFM. So now that we just found out that HFM is 58 degrees, I can see that it's in the same position on that side of the transversal, which means that it has to be equal. EFN, that would be this one right here in the lower corner. EFN also has to be 58 degrees. And the reason I'm going to give this time is because it's vertically opposite from the one that I just found out. And I know that vertically opposite angles are equal, so there's no calculation I need to do. Next one, EGP. EGP has to be 58 degrees. The reason I'm giving is that it's corresponding to EFN, the one that I just solved. It's in the exact same position next to the other parallel line. So that has to be 58 degrees. And last but not least, we have one last angle, HGP. This one has to be 122 degrees. And I'm going to use a different reason now, supplementary angles. Supplementary angles mean that a straight line is going to add up to 180 degrees. So if I see that next to it I have a 58 degree angle, I can take 180, subtract 58, which leaves me with 122 degrees. And that is how I would solve all angles around the transversal line.